Okay, now that we have elementary matrices and some properties about them, we're going to get to some applications. The first application is this theorem here about the equivalence of two conditions that at a glance do not appear to be the same or even related. On the one hand, there's the idea of a matrix being invertible. Well, that's a statement about matrix multiplications and all that. Okay. The simultaneous idea, and again, it appears to be totally different, is the idea of what, a matrix that has a certain reduced row echelon form, in particular a matrix for which the reduced row echelon form is the identity. Now, a matrix A might have this feature, that its reduced row echelon form is the identity matrix, but this does not appear to have anything, at a glance, does not appear to have anything to do with matrix multiplications. This is a statement about matrix multiplications. This is a statement about row reductions. Right? They don't appear to be the same. Now, I will point out here, this is a good time for this, that this is going to be our definition of the word non-singular. A matrix is non-singular if it has this feature, that its reduced row echelon form is the identity. There are equivalent definitions. Well, in fact, this very theorem says that any matrix that has this property also has this property, and so it is an equivalent definition to say that a matrix is non-singular by definition if it's invertible. I find this definition very problematic because we need a term to refer to this property in order to show that it's equivalent to this property. Right? We already have a term for this. The term is invertible, so I need a term as well for the other side. So what this theorem says is that every invertible matrix is non-singular, every non-singular matrix is invertible. I need that to be a statement about math, not a statement about semantics. And along those lines, then, I have to take this as my definition of non-singularity. Okay, so let's move along. Let's do this this proof. This is if and only if, so we've got to go both ways. We've got to start off by proving it in that direction, and then subsequently I'm going to have to prove it in that direction. We will, as indicated here, start off proving in this direction. So I'm going to take it as a given that I have an invertible matrix, and I'm going to try to show that this matrix has to be non-singular. That's going to be my goal. Okay. Right. So, again, we're given that A is invertible. I'm going to start by showing that there's a pivot in every row. Now, why do we care? What does that have to do with anything? Well, let me sort of complete the thought before I do it. The thing is, if there's a pivot in every row, and don't forget this is a square matrix, well, that means that there would be a pivot in every column. And if there's a pivot in every row and a pivot in every column, well, in fact, that would mean that the reduced row echelon form is the identity. That would mean, then, that the matrix is non-singular. So really, this is all I need to do. Once I show that there's a pivot in every row, then I'm done with this first half of the proof. Okay. All right, so how do I show there's a pivot in every row? Well, the existence property for the coefficient matrix. Said differently, I need to show that this always has solutions. If this has solutions for every vector B, then the matrix A has the existence property. That means there's a pivot in every row. And again, therefore I'm done. Okay. All right, so how do I show that this always has solutions? Well, thankfully, I am given that the matrix is invertible. And because the matrix is invertible, I can write down exactly what that solution is. Not only can I show that a solution exists, I can find that solution. Here it is. That is a solution to that system of equations. And this is, again, something you can check directly. Take this and plug it right into there. A times that vector x, where you get A times A inverse times B, that gives you B. And sure enough, that works. So this always has solutions. Therefore, there's a pivot in every row. therefore the matrix is non-singular. All right, now let's go the other way. So at this point, we're going to assume that the matrix is non-singular, and my goal is going to be to show that the matrix is invertible. Okay. This is a trickier half of the proof. It's very, very clever, though. So let's write down what this means. That the reduced echelon form is the identity. Here's where we're going to use elementary matrices. We're not going to think of this as a statement about a process, or what you get when you go through a sequence of steps or anything like that. We're going to think of this with elementary matrices as a statement about algebra. And here it is. This is the row reduction of A. Start with a matrix A. There's a row operation. Then there's another row operation. There's a whole sequence of row operations. Finally, there is a last row operation. This is what a row reduction looks like, right? You take a matrix and do a bunch of row operations. Critically, though, notice that I'm representing that sequence of row operations as a product, one left multiplication at a time, of elementary matrices. Okay, so this is what you get when you row reduce the matrix A. I don't know what these E matrices are. We'll talk about that later. But that's what you get when you row reduce. And the whole point is, because the row reduction is the identity, that reduced echelon form, is the identity. Okay. All right. So this is a huge fact about elementary matrices, is we can take an entire row reduction and represent it as a product of matrices, elementary matrices left multiplied by the original matrix A. Okay, big idea. And now we have an algebraic foot in the door, and we're almost done, actually. We're going to take, in this statement, we're going to take this product of elementary matrices, and we're going to give it a name, call it E. Just plug in like so, so that my equation representing my row reduction gets written a little bit more compactly. There it is, same equation again, just sort of collecting all those elementary matrices into a single matrix E. Very importantly, notice this matrix E is not an elementary matrix, even though I'm using E to represent it. This is not an elementary matrix. It's a product of elementary matrices, right? But it itself is not an elementary matrix. Okay. All right. Well, here's the thing. This means that E is the inverse of A, and therefore A is invertible. And that's what we wanted to show. Right? We assumed a statement about the row reduction, and we concluded that the matrix is invertible, as desired. Okay. All right. Again, who gets credit for this proof? Well, the credit goes to the fact that we're able to represent the whole row reduction with matrix multiplication. That's what allowed us to transform a statement about a process into a statement about algebra, into a statement specifically about matrix multiplication. And of course, matrix multiplication is how we make connections to invertibility. Okay, so elementary matrices are the key tool here. Okay, as it turns out, this also gives us, neat conclusion, this also gives us a method for finding the inverse matrix for an invertible matrix. And the idea is that, well, look, if this E is the inverse matrix, keep in mind that E simply represents all that you did to the matrix A. This statement here is just an observation that if you take all the stuff that you did to A and instead do it to the identity matrix, well, then of course you're going to get A inverse. It's a really clever little observation. So here's how we actually execute that in practice. I've got to do two things. I've got to figure out, given a matrix A, I've got to figure out what sequence of row operations do I do to it to get down to the identity. And once I know that, I've got to take those exact same operations and do them to the identity. And I can achieve that all at once by taking my original matrix that I'd like to invert, put it there, just write the identity right next to it. Start doing row operations. Row reduce the whole thing. And if the reduced echelon form of your original matrix is the identity, then what's in the right side over here will be A inverse. Lovely little method. Okay, so here's an example. Here's a matrix. Now let's ask the question, is that matrix invertible? And if so, what's the inverse? Okay, well, we're going to follow our method. We take this matrix, we write it down, we put the identity right next to it, and we start doing row operations. Now notice, when I'm doing these row operations, I have to do the row operations sort of all the way across, right? I've got to do the exact same row operations on this side that I did on this side. So for example, when I say that I'm going to copy down row 1, well, that means that I take that and put it there. And then similarly, if I say here, I'm going to take row 2 minus 2 times row 1, well, it's that row 2 all the way across minus 2 times row 1. Row 1 goes all the way across, and that is what results in that all the way across. Okay. All right, so repeat, just keep row reducing, and feel free to motivate all your row operations by what is going to turn your left side into its reduced echelon form. Notice that reduced echelon form is the identity. That tells us my original matrix is invertible. Right? If the reduced echelon form is the identity, the matrix is invertible. Okay. Secondly, this thing on the right is the inverse. Okay, and you can check this for yourself. It'd be a nice little arithmetic exercise. Take that and multiply by that, and notice that the product is the identity. Okay. A couple of little algebraic observations. These are just little quickies. One is that the inverse of a product of matrices is the product of the individual inverses. It's kind of what you would expect. There's just this one twist, and you do have to be very careful about that, and that is the matrix that was on the left, its inverse goes on the right. The one that was on the right, its inverse goes on the left. You have to switch the order. Of course, the reason you have to switch that order is that you want to multiply AB times something, and if you want, to get the identity, in other words, if you want to have something be the inverse, you have to order the matrices in such a way that you can actually do the cancellation. I need those to be next to each other so that I can cancel them. And after they've disappeared in a puff of smoke due to cancellation, only then can I cancel those, because they have to be next to each other. Critically, keep in mind, matrix multiplication is not commutative. You can't just move the matrices around in whatever order you'd like. Cancellation, a matrix and its inverse only cancel each other if they are next to each other, namely if they're actually multiplying by each other. Okay, so as a result of this, the inverse matrix has got to have the order switched. Okay. Lastly, a quick observation about the importance of a matrix being square. You recall that this was one of our conditions. A matrix had to be square for this implication to hold, and you recall where we had this in the proof. In the proof, it was because it was square that we could conclude that a pivot in every row implied a pivot in every column. Okay, so I just think it's neat to see that there's an actual easy counterexample showing you how important that is, that if you remove that condition, if you take a matrix that's not square, it is possible to find what you might want to call a right inverse, namely a matrix that you can multiply on the right to get the identity, but that would not be a left inverse. And here's the easy example. This matrix, see, not square, right? But this matrix, if you multiply it on the right by that, you do get an identity matrix. Same matrix if you multiply on the left by the same matrix, you don't get an identity matrix. Very importantly, that's not a 1, this is not the identity. So this doesn't follow. All right, one more application. This is a neat idea. Very practical in many situations, and that is, suppose you want to solve not just a system, but suppose you want to solve several systems. Specifically, several systems where the coefficient matrix is the same on all of them, but where you have a different vector on the right-hand side each time. Right? So, in some sense, it's like the same system over and over again. It's just that, well, but the right-hand side keeps changing. Do you have to row reduce each one individually every time? And the good news is that no. Converting statements about row reductions into statements about matrix algebra let us streamline this dramatically. So here's the idea. Take that matrix A and row reduce it. Now keep in mind, this is our little shorthand for a row reduction. If you have some matrix A, there's a series of row operations that you're going to do. That series of row operations is going to be represented by one elementary matrix after another, listed multiplying by it on the left, and that product you can represent with some product matrix E. And this reducing all the way down to the reduced echelon form means R is the reduced echelon form. So again, very convenient shorthand for a row reduction is that something times the matrix A is a reduced echelon form matrix R. Okay. So here's the neat thing about it. Let's suppose that for a matrix A, let's suppose that you figure out what E is and you figure out what R is. Well, that being done, notice what happens if you take a system of equations and multiply by E on the left on both sides. And notice this is that same system of equations, and I'm just left multiplying by E. Well, EA is R, and so this system of equations then is equivalent to that system of equations. And it's just an observation that this will always work. So if you know what E is, and if you know what R is, then you can take whatever system of equations that you want and just instantly rewrite it as a system which is already row reduced. So really nice. Here's an example of how we might use such a thing. So again, I want to solve that system. Only thing is this these vectors on the right, there's a bunch of them. B1, B2, B3, perhaps more. Okay. Well, I'm not going to do 3 separate row reductions. I'm going to take my coefficient matrix and I'm going to do this process where I go through here. I'll write this down. I'm going to do some row reduction, right, until I get reduced echelon form on the left, right? And of course, consequence of that is that E will be the matrix on the right. So wonderful. Just row reduce this. That will tell you both R and E for that matrix A. So you say you want to solve all these systems of equations. Okay, well fine. Well, don't solve those specifically. Those aren't row reduced. Solve these instead. You already know what R is, right? You know what E is, and now you have a bunch of already row reduced systems. You do have to do a matrix vector multiplication for each one, but that's way less effort than doing a row reduction. So this clever observation here allows you to take what could be a bunch of work and turn it into much less work.